Hello, my dear friend. Today's our topic is Thevenin's theorem. It is prepared by Professor Sudipta Mitra and Professor Sanjay Das. Our object is to understand the basic philosophy behind the Thevenin's theorem and how it will be used to solve the DC circuit. Next, we will explain what will be the advantage of using Thevenin's theorem over the conventional circuit reduction theories. Let us consider the following figure. Our problem is to find the current through the load resistance. Now you may use different technique. For example, you may use mesh current method, then you would require 3 equations to solve it. You may use nodal voltage method, then you would require 2 equations to solve it. Or you may use superposition theorem, then you would require many equations, and you know that. So now our problem is to, if we change RL, that theorem will be used for fixed RL. Now suppose if we change the RL, then if you ask to calculate the current through the load resistance, then what you have to do? You have to apply this theorem again and again for different values of RL. Now how we can avoid this tedious mathematical work? So to avoid this, what we will do, we will fix the part of the circuit within the fringe box, that is within the fringe box. If we replace this part of the circuit look like this, then so it is RTH, it is VTH, then for different value of RL you can calculate the load current, and that calculation will be easier. So this reduction can be done using Thevenin's theorem. So what Thevenin's theorem tells, that you can replace any linear active bilateral network look like this, that is voltage source VTH in series with RTH. So how you will calculate RTH according to Thevenin's theorem? So what you have to do, first replace all the internal resistance of the sources, that is it may be voltage source or it may be current source, by their internal resistance, and remove the load and see it from the load side. So see it from the load side. This is our circuit. So within this box, this is our linear active bilateral circuit. So we replace all the source by their internal resistance, and we look from the load side. We remove the load and we look from the load side, and we calculate the resistance. That will be RTH. And what is VTH? Just open the load and voltage source and current source will be there, and measure the voltage, that will be the VTH. So this is our Thevenin's theorem. So what are the steps to calculate the VTH, RTH, etc.? So first, step 1, disconnect the load resistance RL from the circuit as indicated in figure C. So disconnect the load from the circuit. So this is our circuit within the box, this is our circuit, and this is our load side. So first we disconnect the load and complete the DC circuit, that is voltage source and current source will be there. Now step 2, measure the voltage here. So voltage source and current source is within the box, so this is our original circuit and this is our load side. So remove the load and measure the voltage here. So that voltage will be the VTH. Now for RTH, what you have to do? So this is step 3. For RTH, what you have to do? So replace the voltage source and current source by their internal resistance. So within this box, this is our circuit, this is the load side. So what we will do, we will replace the voltage source and current source by their internal resistance, and we will remove this. That will be shown that is shown in figure 5. So this is passive circuit. Actually this is the passive circuit, this is the load side. So we remove the voltage source and current source and replace it by their internal resistance and see it from the load side. That resistance will be the RTH. Now for the step 4, within step 4 what we will do, we will see it from the load side and we will see how many resistance exist between these two terminals, and so now we know the value of VTH from step 2, and from previous step, that is step 4, we know the value of RTH. So replace this box, that means this is our original circuit, replace this box according to Thevenin's theorem by voltage source, that is VTH, and the series resistance RTH, and this AB or the load terminal. Now in step 7, connect the load resistance between the terminal AB. So what will be the load current? IL, that will be equal to VTH RTH plus RL. So from Ohm's law you know that VL, what will be VL, that you also know. So this is the formula of VL and this is the formula of RL. So see what is the advantage of using Thevenin's theorem. So this VTH, this RTH, that is independent of load resistance RL. So for different type of load, your VTH and RTH will be remain same. So you can calculate IL for different load, just replace the value of RL, so that will be your load current. So this is the biggest advantage of using Thevenin's theorem. So these are the advantage. First advantage, Thevenin's theorem, that reduce the calculation or reduce the labor of the calculation of load current, load voltage, power, etc. And next advantage is that with the help of this theorem, one can choose the load resistance that result in the maximum power transfer to the load. So see, so if you change this RL, suppose you change the RL from 0 to infinite, then you calculate the power, and then you will see that once upon a time this power will be maximum, then it will be reduced. So using Thevenin's theorem you can calculate the maximum power. So this is our example. Let us one example. So this is the circuit, voltage source is there, current source is there, all the resistance, value of resistance that is given. So find the current through this resistance RL, that is 1 ohm. So find the current through the 1 ohm. So what will be our first step? So we just remove the load and measure the value of the voltage here. So to calculate the voltage, you can use mesh analysis, you can use nodal analysis, or you can use superposition theorem. So here suppose we use mesh analysis or nodal voltage. So what will be the mesh equation? So add node equation, add node C. So this current and this 2 ampere. So this is I1, let this current is I1, let this current is I2, this is 2 ampere that is given. So if we apply KCL at node C, so summation of the current, that will be 0. So 2 plus I1 plus I2 equal to 0. So I1 is, suppose this node voltage is VC. So I1 will be this potential minus this potential divided by this resistance. So that's why this potential is 3 volts. So it is 3 minus VC by 3 plus, so this current I2, this current will be, so this I2 current that will flow from here to here. So this potential, that is at ground potential. So that's why it is 0 minus this potential is VC. So 0 minus VC by 6 equal to VC. So if we solve this, so the VC, that will be 6 volt. So from here you can calculate I1. So this potential minus this potential by this resistance. So you know this VC, you know this VA, that is 3 volt. Now you can calculate the current I1 and I2. So once you know the value of I1 and I2, then you can calculate this VAB using this equation. So VAB means VAG minus VBG. So AB means, so with respect to ground this voltage, with respect to ground this voltage. So if you define, so this voltage is the difference of these two voltage. So with respect to ground, this voltage A VAG, that will be equal to 3 volt. With respect to ground, potential of A, that is 3 volt. And similarly with respect to B, with respect to G, potential of B, that will be equal to this potential drop. So this potential drop means this I2 into 2. So I2 into 2 means here it will be 2 volt, because I2 equal to 1, so it will be 2 volt. So from here you can calculate, from here you can calculate VTH. So VTH, that is 1 volt. Now step 4 is for calculation of RTH. So for RTH, what you will do, just replace the voltage source and current source by their internal resistance. And in our example we assume that our voltage source, that is ideal voltage source, current source, that is ideal current source. So for ideal voltage source, internal resistance will be 0. So just replace the voltage source by the internal resistance, that is 0, short circuit. And this is our ideal current source. So ideal current source, resistance will be infinite. So just open it and remove the load and measure the resistance from load side. So we will see it from this side. So that means we will calculate the resistance across these two terminals. So that means it will be R1, this R1 and this R3, that will be in series, because this current is 0. So current will flow from here to here. That means this and this resistance will be in series. So this is series combination, and within and this, with this series combination, this resistance R4, that will be in parallel. So our result will be 1.55 something like this. So now step 5. So this will be the Thevenin's equivalent circuit. So this box, this is the load side and this box is the remaining part. So we replace the remaining part with VTH and RTH. So VTH is 1 volt and RTH is this 1.55 something. Now we can calculate IL. So step 6, for step 6 you can calculate the branch voltage. So once you know the value of this current, then you can calculate this voltage, you can calculate this voltage, anything else. So this is the voltage. So this is our, so this is the end. So assume you understand the Thevenin's theorem. So thank you. Okay.